strong P, PAB, PST. Okay, so when I first saw this, I was thinking, okay, but this looks like a natural transformation, but it's between something else. I mean, this is like a different category. How can you have a natural transformation where you have profunctors, right? And then I figured out that the only place, I knew very little about category theory, but I knew the Yoneda lemma. And the Yoneda lemma is one place in which you have this for all. It's just like a pattern recognition. Okay, here's for all, here's for all. Then maybe Yoneda lemma is relevant to figuring out the lens, okay? So let me explain what a Yoneda lemma is. So Yoneda lemma says that there is this special functor called the reader functor that is just a type of a function from A to X. So it's a functor in X. A is just a parameter. There are two types, A and X, right? It's actually a profunctor, but you know, it's looking just at the X part, it's a functor, right? And here's like the definition of why it is a functor, instance functor. I can define fmap for it, how to lift a function, right? Now, Yoneda lemma says that if you have any functor f, then first of all, you can get to this functor f from the reader functor. So reader functor is a very special functor because it has natural transformations to every other functor. And the set of these natural transformations between these two functors. So now remember, two functors, natural transformations, which is a polymorphic function, between two functors, right? The set of these natural transformations is equivalent to the value of this functor at the object A, okay? And here below it's written as a natural transformation. And natural transformations for all x. This is the reader of x. This is fx. And this is equivalent to f of a. Now, quickly, the intuition behind this. The left-hand side is a function that takes a function. Okay, so it's a higher order function, which is polymorphic in x. The right-hand side is what we call data structure. It's like, okay, it could be a list, right? Take type A, you get a list of A. So there are two very different representations. One is what we normally call data. The other is function, a polymorphic function, polymorphic higher order function. These two representations are totally equivalent. And this is what is great about the Yoneda lemma in programming, because sometimes you want to use a different representation for your data type for performance reasons or for reasons like in this case it will be because it composes better. Okay? So that's a great point of Yoneda lemma. And here's a little proof that the Yoneda lemma works, and actually it's kind of in Haskell it's almost trivial why this should work. Okay, but I'm not going to go into the details in there because I'm interested in the special case of Yoneda lemma, where the second functor, so it's a natural transformations from a reader functor to some arbitrary functor f. I can replace this arbitrary functor f in particular with another reader functor, right? And then I get this formula at the bottom, which is the Yoneda lemma for the reader functor here, right? It's a different reader. It's a reader from B. The first reader is from A. The second reader is from B, right? And if so this is my fx. right? If I replace x with a on the right-hand side of the Yoneda lemma, I will get fa is function from b to a. All right? So it's b to a. So this is a really a huge simplification. You have like a function that takes a function and returns a function, and it's polymorphic in x, and it's totally equivalent to a function from b to a. Notice that they are reversed. Like a is here, b is here. Here they are reversed. And this is called, well, this is just a special case of Yoneda lemma, but it's used in so-called Yoneda embedding, so I call it Yoneda embedding. And now, remember, I wanted a polymorphic thing that's polymorphic in profunctors. So let me make the next abstraction and say, okay, how can I use a Yoneda lemma so that the for all actually takes a functor rather than a type? Well, from the point of view of category theory, that's a very simple thing, you know. Functors form a category. What kind of category it is? Functors are objects in this category, and arrows in this category are natural transformations that I mentioned before. Because natural transformations go between functors, okay? So they form a nice category. And since they form a nice category, the Yoneda lemma applies to them as well. So I can take the same Yoneda lemma, replace my x with a functor, and I replace my functions with natural transformations, and I get a Yoneda lemma in the functor category. So above is Yoneda lemma. Here's the Yoneda lemma in the functor category. You see what changed? I just renamed these things so that they look more like functors. I replace them a and x with g and f, right? And I replace arrows with squiggly arrows, right? Which is natural transformations. So the mapping from natural transformations between functor g and f, there's a natural transformation between functors h and f, and the result here, this is equivalent to a natural transformation from functor h to g, okay? And I have, finally, this for all f, where f is a functor, okay? So I'm getting very, very close to lenses, but not quite yet.